Well, let's talk about these solutions. We've learned how to calculate concentrations and do some things with concentrations. But let's talk about the actual solution. So let's think about two familiar aqueous solutions. And remember that aqueous means that water is the solvent. So salt water and sugar water. And you've probably had these at home at one time or another. You can take a glass of tap water and pour some salt into it and stir it, right? And the salt dissolves, it appears to disappear. You can do the same thing with sugar. We know that the sugar and the salt did not just disappear, because if we taste the water, you can taste that the sugar or the salt is there. If you let the solution sit until all the water evaporates, the salt will be left, or the sugar will be left. My number 4 son, who was born on Mole Day, loves to experiment. And so yesterday, after he had gone to a friend's house, we were cleaning up the kitchen and noticed an interesting spill. And he had been trying to make large salt crystals, and so he'd made a rather concentrated salt solution and heated it up and then spilled it all over the place. And a lot of it had evaporated and left these little tiny salt crystals all the heck over the place. I mean, it was just, wow, dude, I can't believe you made this mess. I should believe it. He does it all the time. But, you know, he's 13, and he likes to experiment. He's going to do great things if he doesn't kill himself before he grows up. But, you know, here we go, saltwater solutions. And it evaporated, and bang, there's the crystals. I probably should have taken pictures, but I didn't. So why do things dissolve? There's a competition between interactions. So a sodium chloride crystal is made of sodium ions and chloride ions. And why do they stick together? Because we have a positive ion and a negative ion, and they're like magnets. They're attracted to each other. So there's a force of attraction between the particles. That's why salt is a solid at room temperature. Why is water a liquid at room temperature? Why don't all the molecules fly away? Because there are attractions between the water molecules, and we'll learn more about those later. So we have solute-solute interactions. Those are interactions between the solute particles. We have solvent-solvent interactions between the water molecules. We can also have solvent-solute interactions. So those are the interactions between water molecules and the salt ions. And if the attractions between the solvent and the solute are strong enough, then the solute will dissolve. It will separate into smaller pieces and make a solution, a homogeneous mixture. We have to talk a little bit about water. There's an uneven distribution of electrons within a water molecule, and we'll learn a lot more about this later as well. But the electrons in the covalent bonds between the oxygen and the hydrogen are more attracted to the oxygen than they are to the hydrogen. And the result is that one end of oxygen, the oxygen end of water, has a slightly negative charge. And the hydrogen end of water, a water molecule, has a slightly positive charge. It's not an ion, but it's got a slightly positive charge on one side and a slightly negative charge on the other side. This is important for dissolving ionic compounds. When we put sodium chloride in water, there's still the attraction between the sodium ions and the chloride ions. To make it dissolve, we have to replace that attraction with something else. And so the sodium, being a positive ion, is attracted to the negative end of the water molecule. The chloride ion has a negative charge. It's attracted to the positive end of water molecules. And what happens is that many water molecules will surround the sodium ion with its positive charge and turn their negative side towards the sodium ion, essentially replacing the attraction that it felt for the chloride. And the chloride's attraction for the sodium ion gets replaced by several water molecules clustering around it with the positive sides towards the negative ion. And as a result, the ions are able to separate from each other and move freely throughout the water solution. Any questions? Stunned silence. It's okay. There are two basic types of solutions. There are electrolytes and there are non-electrolytes. You've probably heard the word electrolyte in reference to sports drinks like Gatorade and Powerade. You know, you've been exercising and sweating a lot, you need to replenish your electrolytes. Electrolytes are soluble ionic compounds. When they dissolve in water, they will form a solution that can conduct electricity. So soluble ionic compounds form solutions that will conduct electricity. Here's an example. If you take a light bulb connected to a voltage source and you take the wires and instead of connecting them or putting a switch here, you stick them in water, nothing will happen until you put some salt in there. If you put some salt in the water, then the light bulb will light up because the sodium and the chloride ions in the water can carry the electric current from one electrode to the other. Their electricity is the flow of electrons. And the circuit needs to be complete in order for the electricity to flow. If there's a break in the wire, electricity doesn't flow. Non-electrolytes also dissolve in water, but they don't form solutions that conduct electricity. This includes most molecular compounds like sugar. The particles do not have charges, and so they can't carry electrical current. So if you do this with sugar, the light bulb will not light up. Electrolytes conduct electricity, non-electrolytes do not. Here we have a space-filling model of sugar, sucrose, table sugar. And we see that the sugar molecule also has a lot of hydrogens and oxygens on it. And there is a charge imbalance in these bonds as well. And so we do get some attraction between the negative end of water and a slightly positive charge on the hydrogen ions, and vice versa, the positive end of the water and the slightly negative end of the oxygen. And so the sugar will dissolve in water, but there are no ions involved, and so it doesn't conduct electricity. But the sugar molecules have little clusters of water around them, replacing the interaction between the sugar molecules that made it a solid at room temperature. We've talked about acids. We learned how to name them and write their formulas. And we said that acids are molecular compounds, but they ionize when they dissolve in water. They form hydrogen ion and an anion, like chloride or perchlorate or whatever it is. What happens is the molecules get pulled apart by their attraction for the water molecules. And we divide acids into two categories, strong acids and weak acids. A strong acid will ionize completely. The fact that it's strong has nothing to do with its concentration or how corrosive or dangerous it is. It has to do with the percent ionization. How many of the molecules ionize? For a strong acid, basically all of them do. For a weak acid, only a few, a small percentage of the molecules will ionize. So here we have HF. This is a weak acid. It forms some hydrogen ions and some fluoride ions, but mostly we'll see hydrogen fluoride molecules floating around in the water. Acetic acid is also a weak acid. Here we have an illustration of acetic acid in water. And so there's a hydrogen ion, there's an acetate ion, but most of these are intact molecules of acetic acid. And so that's a weak acid. There should be a slide here that tells you which ones are which, and it isn't here. So these are the strong acids. So there's 6 of them. These are the strong acids. So you remember those 6. And any other acid is a weak acid. So HCl is a strong acid. It separates completely into hydrogen and chloride ions. In solution, there are no hydrogen chloride molecules present. That's true for the strong acids. For the weak acids, it's mostly the intact molecules. So we just talked about electrolytes and non-electrolytes. Electrolytes can be strong or weak. And this is the same use of the words strong and weak as with the acids we just talked about. A strong electrolyte dissolves completely as ions. It ionizes completely, just like a strong acid does. And it will conduct electricity strongly. The light bulb will glow brightly. In a weak electrolyte, it dissolves mostly as molecules and only partially as ions. So weak acids are weak electrolytes. They form some ions, but mostly they're molecules. And so these solutions will conduct electricity weakly. The light bulb will just be dim because it can conduct electricity, but it doesn't do it very well because there's not as many ions. Any questions? So here we have a non-electrolyte, and we have this conductivity apparatus. This is a sugar solution, and we put the sugar solution in water. It dissolves just fine, but it doesn't form any ions, and so the light bulb doesn't go on. Here we have a weak electrolyte, acetic acid. When it dissolves, it forms a few ions. It forms enough ions that the light bulb glows a little bit, but it's not very bright. In a strong electrolyte like sodium chloride, all of the ions separate from each other. There are a lot of ions present, and so it conducts electricity well. Any questions? Yes?
What is that experiment called?
It's a conductivity experiment. And I wanted to do a demo. I actually tried to do this last year, and the apparatus wouldn't work. And then I forget to mess with it until I'm in lecture thinking, oh, shoot, I wish I had that with me right now. If you remind me after lecture, I'll get it out, and we'll try it during lab. But you have to remind me. Yesterday they didn't, and I forgot again. Because I have a brain like a sieve. It's gone. So when an ionic compound dissolves in water, the anions and cations separate from each other. This is called dissociation. Association is when things come together. Dissociation is when things move away from each other. So when we have something like sodium sulfide, this is an ionic compound. AQ here tells us that it's dissolved in water. An ionic compound dissolved in water is going to ionize completely. In this formula, there are 2 sodium ions, and so when it dissociates, it forms 2 sodium ions. And there's 1 sulfide ion, and it'll form 1 sulfide ion. Because these ions are separate from each other, we have to include their charges. When they're together as a compound, we don't write the charges. They still have charges, but it gets too complicated. So we don't write charges in compound formulas, but if we're doing ion formulas, we do. If you have a compound containing a polyatomic ion, like sulfate in this example, polyatomic ions do not come apart when they dissolve in water. So the sulfurs and the oxygens are covalently bonded together, and they're not going to come apart. Just the sodium and the sulfate are going to separate. And so we'll have 2 sodium ions and 1 sulfate ion. Any questions?
How do they separate?
Well, they separate because the water molecules come and surround the sodium ions, and they surround the sulfate ions and make them feel comfortable.
So, no, but I mean, how if you wanted to separate that.
Oh, if you wanted to separate the sulfur and the oxygen and sulfate, you'd have to do that with a chemical reaction. Yeah. Yes?
How did they figure out that happened? Just out of curiosity.
How did they figure out that they stay intact? You know, I don't know off the top of my head. I don't know. But yeah, we're going to talk some more about this, and then if it's still puzzling, ask me again at the end. Any other questions? Well, how do we know if an ionic compound is going to dissolve? When they do dissolve, the solution contains ions, it's a strong electrolyte, but some ionic compounds do not dissolve in water. And so if it dissolves, we say it's soluble. If it doesn't, we say it's insoluble. This is not there's not a sharp line here. It's you know, kind of a gray area in the middle. Because even what's considered an insoluble compound will dissolve a little bit, right? But it's so tiny that it doesn't really matter. And so there's not a real clear distinction there. If we look at silver nitrate, there's the formula. We take solid silver nitrate composed of silver and nitrate ions. That will dissolve in water and form an aqueous solution. The silver ions and the nitrate ions will separate just fine. But if we take silver chloride, AgCl, and put it in water, mix it up, you can stir that all day long. Only a teeny tiny fraction of it will dissolve. It's not something that you would be able to notice just by looking at the solution. You'd look at it and you'd say, oh, it looks like it didn't dissolve at all. That's the same amount of stuff I put in there. It's insoluble. So you might be wondering, well, why are some things soluble and some things insoluble? Unfortunately, the answer to that question is rather complicated and definitely beyond the scope of this part of the class. So at this point, the best we're going to do is we're going to use some rules that have been developed empirically, meaning experimentally. So they took different ionic compounds and put them in water and stirred them up to see, does it dissolve? Does this one dissolve? Oh, that one doesn't, that one doesn't. And they just tried a whole bunch of them. And so this is an empirical method, and we've got some rules based on those results. So here are the rules. You need to memorize these. So there's two parts to this table. The top lists compounds that are generally soluble. If the compound contains one of these ions, it's probably soluble. And then over here, any exceptions are listed. So if it contains one of the group 1A metals or ammonium, the compound is going to be soluble. No exceptions to that one. If it has nitrate or acetate ion, it's going to be soluble, no exceptions. These are halides, chloride, bromide, and iodide. Those are generally soluble with 3 notable exceptions: silver, mercury, and lead. So if you have lead chloride, lead 2 chloride, it's not going to dissolve. Sulfate compounds are generally soluble except with these guys. Here we've got the lead and the silver again, and then we also have strontium, barium, and calcium. The bottom half lists ions whose compounds are generally not soluble. So hydroxide compounds and sulfide compounds are generally not soluble. Now this exception is redundant, because the way I recommend using a table like this is you go from the top and you work your way down. If you get down here and you had lithium, see, here's an exception, lithium hydroxide is soluble, but you should have stopped up here. If it's got lithium in it, it's soluble, you don't have to look any farther. So this is a redundancy of that rule. Here's the exceptions for sulfide, calcium, strontium, and barium. Notice those are the 3 that are an exception up here. And so there's some common things going on here. Hydroxide with calcium, strontium, or barium, this is called slightly soluble. I mean, it dissolves a little bit. So we're not going to call it insoluble, but not very much. And then carbonate and phosphate compounds are generally insoluble unless they're with one of those guys. And again, that's a redundant rule there, because if you've got one of these, it's going to be soluble no matter what the other ion is. So let's do some examples here and predict the solubility of nickel to sulfide. So we go over here to the table, and we're going to look for those two ions. We're looking for nickel and sulfide. No, 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 no. Oh, here's sulfide. Sulfides are generally insoluble, except with calcium, strontium, or barium. But that's not one of those exceptions. So this one is insoluble. So if we had this in a chemical reaction, the state of it would be a solid. It's not going to be aqueous because it's not soluble. So S for solid. How about magnesium phosphate? Looking up here for magnesium and phosphate, not seeing anything, not seeing anything. Oh, phosphate. Phosphate compounds generally insoluble and not one of the exceptions. So is this aqueous or a solid? It's a solid. It's not soluble. Lithium carbonate. Well, again, start at the top. Oh, lithium. Lithium compounds are soluble, no exceptions. We don't need to look any further. This compound is soluble. So its physical state in a reaction would be aqueous. It would dissolve in water. How about ammonium chloride? Is that going to be aqueous or a solid? Aqueous, because ammonium compounds are always soluble. Ammonium's right up here. Okay, any questions? Yes?
Mercury's not diatomic, right?
That is mercury 1, and it's a diatomic ion. So mercury 1 is Hg2, 2+, and mercury 2 is Hg2+.
So does that mean only the diatomic version of that?
Only the diatomic version, yeah.
Okay.
Yeah. And we probably won't run into that one much, but it is there. Mercury's just got to be a little strange. Any other questions? So I think the best way to memorize these rules is to use them, okay? We're going to be doing some equations and things where we have to predict the solubility of ionic compounds. Don't just automatically look at the chart. Try to remember first. Think, oh, I think ammonium was, I think those were soluble. So make your best guess first, and then check yourself on the chart. If you do that every time, after a while, you'll remember the chart without even really trying very hard. That's the only way I know remember the chart, because I just keep doing these examples in class. Okay, precipitation reactions. We saw a couple of these types of reactions when we did the that copper cycle observation lab, and we had things changing colors. So in a precipitation reaction, we have two solutions being mixed together. Here we've got one clear solution, clear colorless solution, pouring it into another clear colorless solution, and bang, a solid forms. That solid that forms is called a precipitate. It's called a precipitate because it falls slowly through the solution, just like precipitation does. They're predicting rain today. The meteorologist says it's precipitation, right? Snow is precipitation. It falls. So this is the precipitate. Here's the equation, which I can't read on my screen. It's lead iodide and potassium nitrate. And we can predict which of those is the precipitate based on those rules of solubility. So let's look at how we would predict what the products are. We need to look at the original compounds. So we had potassium and iodide in solution. If we look at the rules, that's going to be aqueous. So we have potassium and iodide. And then we have lead 2 and nitrate. And that's a soluble ionic compound. So we've got lead 2 and we've got nitrate. So the possibilities here are that we're just going to swap ions. In order for a precipitate to form, it has to be an ionic compound composed of a cation and an anion. So we're going to look at the combination of potassium with nitrate and of lead with iodide, and then we're going to predict whether these are soluble or not. Potassium nitrate. Try to think through that table. Well, potassium is on that first row, right? Potassium compounds are soluble. So this can't be the precipitate. Oops. So that one's aqueous. And then lead iodide, okay, we went down, there was the potassium, lithium row, and then there was nitrate and acetate, and then below that were the halides, chloride, bromide, and iodide, generally soluble, except with silver, lead, and mercury. And so here we have the lead 2 with iodide, and so this is going to precipitate. It's going to form a solid. Okay, so I have this imaginary land I call Mrs. K's Chemistry World. I think it's a really fun place. Other people are not so thrilled with it, but I'm going to tell you about it anyway. And so this is how I see precipitation reactions in chemistry land. So here in this container, we have cations and anions. And I've told you before, I think of the metals, the cations, as being masculine, and the anions or the nonmetals as being feminine. And so here we have a guy and a girl, and they're going to a party together. They're just friends, but they're going together. And here is a guy and a girl, and they're going to the party together. They get to the party, and they're mingling around, and then lead sees iodide, and he's just blown away. She is just so amazing, right? And he just goes over to her, and she likes him too, and they've just like this instant chemistry between them, right? They form a solid. They're not mingling at the party anymore. They're stuck on each other. That's the couple on the back porch necking for the rest of the party, right? They're not talking or playing Trivial Pursuit or doing what everybody else is doing, okay? Because there's this strong attraction between them. How do you predict the attraction between two individuals? You can kind of predict, but you can't necessarily just say, oh, well, this person and that person, they're just going to hit it off instantly, right? And so, just looking at different ions, you can't really predict it either, but that list of rules will tell us, oh yeah, lead and iodide, we should have seen that coming. They're going to go off together. Okay, so that's my analogy for precipitation reactions. So sometimes you go to a party and nobody is really attracted to anybody else, right? So here we have potassium iodide and sodium chloride. So we have potassium ion and iodide ion going to the party. We've got sodium ion and chloride ion going to the party. And then they get to the party and they mingle around and they're like, this is kind of fun, but there's no sparks, right? There's no chemistry. So there's not actually a chemical reaction that occurs. It's just a physical change. There was mixing. There was mixing that involved, but there's no changes. There's no new solid formed. And so the result of that is no reaction. Any questions? So for those of you who like steps, lists of instructions, here's your list. we need to be able to write precipitation equations, write equations for precipitation reactions, and this is how we're going to do it. You need to have the formulas for the two reactants, and then below that, write the formulas of the products that could form. So I'll show you an example, it'll become clear. Then look at the solubility rules to decide which of the possible products is a solid. Maybe they're both solids, or maybe they're both not solids. Maybe they're both soluble. If all the products are soluble, then you just write no reaction, you're done. That's always fine. If one or both of the products are insoluble, then you have to write the formulas. You have to indicate which one's a solid, which one's aqueous, and then you need to follow through and balance the equation. So let's put those into action. Write an equation for the precipitation reaction that occurs, if any, when ammonium chloride and iron 3 nitrate are mixed. First thing is we need the formulas for the reactants. And we're going to practice our nomenclature here. So, ammonium chloride. I'm going to write my equation up here, and below it, I'm going to write my ion formulas with their charges. So ammonium is NH4+, because I memorized it. Chloride is Cl-. Chloride's in group 7A of the periodic table, and so all those guys have a -1 charge. So we can look at the charges on these, and that tells us how to put them together. NH4Cl, I just need one of each. This question doesn't specifically say that these are solutions. So if I go to the list of solubility rules, ammonium is in the first row, always soluble, and so this would be aqueous. The next compound is iron 3 nitrate. So I need to write the formula for iron 3, that's Fe3+, and nitrate is NO3 -1, just because that's what it is. And then I look at the two and their charges so that I know how to put them together. And I get FeNO3, 3. I need 3 of the nitrates to balance the charge on the iron 3. Is that compound soluble? Yes, it is. The first row, lithium, potassium, sodium, and ammonium. The second row, nitrate and acetate. This has nitrate in it. No exceptions. So this one's aqueous. So those are the reactants. Now I need to have these guys meet each other at the party and see if anything happens. So iron and chloride, I'm going to see how well they get along, and ammonium and nitrate. It has to be a positive ion and a negative ion, okay? Because these are electrostatic charges, right? This is where the analogy with real life breaks down, because you could have two guys going off on the back porch. It could happen. Pardon me? Yeah, it's going to be a metal and a nonmetal. You have to have a cation and an anion. The ammonium is the one you have to watch out for because it's not a metal, but it is a cation. So you have to have plus and minus. So we've got ammonium and nitrate, and I'm going to see how they work out together. So NH4 plus and NO3 minus, that's one possible combination. The other possible combination is the iron and the chloride. And we write the iron first because of convention. Like on a wedding invitation, it's Mr. and Mrs. It's always the cation first and then the anion. So before I bother to write formulas for these, I'm going to look at the solubility rules and decide if these are soluble or not. So what about ammonium and nitrate? Is that going to be soluble? Yeah. Ammonium compounds are always soluble. So that one's going to be aqueous. How about iron 3 and chloride? Chloride compounds are generally soluble. The exceptions are lead, silver, and mercury. This is not an exception. This one's also aqueous.
So not
So nothing happens. They mix, but no new compounds are formed, and so this is no reaction. Or sometimes we get really lazy and we just say NR, no reaction. Any questions? Just because you mix stuff together doesn't mean a chemical reaction occurs. Let's do another one. Write an equation for the precipitation reaction that occurs, if any, when sodium hydroxide and copper 2 bromide are mixed. Well, again, we need the formulas. So we'll start with the ions. Sodium is Na+. It's in group 1A. It's got +1 charge. Hydroxide, OH-, because that's what its name is. So putting those two together, I would get NaOH. The rules of solubility tell me that this is going to be soluble because all sodium compounds are soluble. Copper 2 bromide. Copper is Cu. The 2, Roman numeral 2, tells me the charge. And then I have bromide, it's Br-. And so this is going to be CuBr2. Is this one soluble? It was the third row, chloride, bromide, iodide, soluble except for lead, silver, and mercury. This one is soluble. There's my reactants. Now I have to swap partners and see what I get. So the copper and the hydroxide, the sodium and the bromide. It doesn't matter which compound you list first in the products, but within the compound you have to list the cation first. So I'm going to do Na+ with Br-, and then I'm going to have Cu2+ with OH-. Compound between sodium and bromide, will that be soluble? Yeah, because sodium compounds are always soluble. So this one's going to be aqueous. How about copper with hydroxide? That's going to be insoluble. We go down to the bottom half of the chart. Hydroxide compounds are generally insoluble, except with calcium, strontium, and barium, they're slightly soluble. This is not an exception, so this is going to be a solid. Darn, now we have to finish this. Okay, so put them together, the sodium and the bromide, and that's aqueous. I'm writing this formula based on the relative charges. I've got 1+. Down here, this is not part of your answer, but this is part of showing your work. And I really think you should do this because otherwise you're going to make a lot of mistakes. I see it a lot. I wouldn't just write this out without writing stuff down until you get really good at it. So the copper 2 and the hydroxide, we're going to get CuOH2, and that's going to be a solid. Any questions? Are we done? No, we have to balance it. What's an ion that is not balanced? Excuse me. Sodium's balanced. The bromide isn't. So here we got Br2, 2 bromides, and here we only have 1. So we need to put a 2 here to balance the bromides. But that messed up sodium, right? Now we have 2 sodiums and only 1 over here. So I'll put 2 over here. And then I've got copper. There's 1 copper and 1 copper. I've got 2 OHs. And, oh, cool, 2 OHs. Magic, yeah. So this part down here, I would encourage you to write that, but that's not part of the answer. Any questions?